So each time we have a problem where n is more than 1, it is going to be a sampling distribution problem. Every time we have a sampling distribution problem, we have to check our conditions. So depending on whether it's a means or proportions problem, that will tell us what conditions we're checking for. Or I should say how we check them, because for both means and proportions, we will be checking for the normality of the sampling distribution. And we'll also be checking for random selection or random assignment of treatment. Right? So if we're doing a random sample, it has to be from the population of interest, who or what we're interested in studying. So for means problems, we have 3 different methods, 2 of which came from Unit 2. One is we could be told that the population is normally distributed, or if we have the individual data values, we could make a normal probability plot and see if it's approximately linear, which will tell us that the sampling distribution will be approximately normal. And then the method that we found out in the 3rd unit here in sampling distributions, that if n is large enough, as n gets bigger and bigger and bigger, the sampling distribution will become approximately normal. And so our magic number is 30. So when n is at least 30, the central limit theorem applies. And then our second check, simple random sample from the population of interest. For proportions, there's only one check, but there's 2 parts to it. One is that our n times p, our sample size times the proportion of the population, has to be at least 10, and also n times 1 minus p, the proportion of the population that doesn't have the characteristic that we're looking for. They both have to be at least 10. And then again, also a simple random sample or random selection of people in the experiment. Okay, so let's do a practice problem. And so milk experts believe that 70% of all U.S. adults who drink the milk from their cereal, believe that 70% of all adults drinking milk from their cereal. And so 1,012 adults were sampled, and it turned out that 67% of that sample responded that they did drink the milk. Okay? So we want to find the likelihood that if the claim was true, that the sample would be 67% or fewer. Okay, so you're not going to be prompted into the conditions and the center and the spread. You'll just kind of have to know that. And so we're going to check our conditions in this case. So our population is all U.S. adults. That's our population. What about them are we studying is, do they drink the milk from their cereal or not? So when they answer that, it's either yes or no, so that's categorical. And so this is going to be a proportions problem. So we identify that first. Okay. Now we start off with our conditions. And so we're going to check for normal. And we said that those conditions for proportions were that n times p and n times 1 minus p both had to be at least 10. Okay, so let's check that. So let's list out what we know and what we don't know, our parameters and our statistics. So what we know, that someone kind of magically knew that the true proportion of people in the U.S. who drank their milk was 70%. Then, from our sample, which is where statistics come from, our sample size was 1,012. And our p-hat, our sample proportion, was 67%. Sometimes they'll just give you the number of successes, and you'd have to divide that by the sample size to figure out the true proportion. But they told us it was 67%. So this is kind of my bank where I know to look for some things. So now, for our normality check, n times p, and so I just substitute in, n is 1,012 times 0.67. And so that's going to be about 670, 680. I calculated if I wanted to take that time, and so it's about 680. And that is greater than or equal to 10. Our n times 1 minus p, in other words, 1,012 times 0.33, 1 minus 0.7 is 0.3. That's about equal to then, I don't know, about 340, 330, something like that. And that's also more than 10. So we've shown that as normal. And then a random selection. And this says a random sample. And so we can say stated. So this takes care of our conditions with normal and random. Okay? So now we're going to find the center of our sampling distribution and the spread of our sampling distribution. So for our center, that's going to be equal to mu. Again, it's a proportions problem, so it's mu of p hat. And that's going to be equal to p, that's on your formula sheet, which is equal to 0.7. Then our spread, and that for a proportion problem is sigma of p hat, and that is equal to the square root of p times 1 minus p over n. And so that's going to be equal to 0.7 times 0.3 over 1,012. And we're going to take the square root of that. So that's about 0.014. Okay? So now we have everything we need to make our sampling distribution. And I'll make that, and I'll come right back. So the center of our sampling distribution, 0.7. And then every time we go up a tick mark, we're going to add 0.014. Every time we go to the left, we're going to subtract 0.014. So this is our sampling distribution of size n equals 1,012 for a population that has a proportion of 0.7. Okay. And so now, to answer the question, what is the likelihood that if the expert's claim is true, that they would receive a sample of 1,012 adults in which 67% or fewer, again, you can have a whole long problem with maybe just 1 or 2 words will tell you the direction that you're going to shade. So we're going to find 67% on our drawing. Okay, it's pretty far to the left, just to the left of 0.672, or fewer. And so that's going to be smaller. Now, all of a sudden, we've done the hard work, and now this becomes a Unit 2 problem, just finding the area under the curve. And so this would be norm CDF. So we shade, we start at negative infinity, we stop at 0.67, and we have a mean 0.7, u of p hat is 0.7, and our sigma of p hat of 0.014. And that ends up being a likelihood of about 0.016. So there's a 1.6% chance that they would have gotten 67% or fewer responding if, in fact, the true proportion was 70%. So that seems pretty unlikely. And so it's based on your answer for part A. Do you think the expert's claim is correct? Why or why not? Seems like it wouldn't be correct because it just seems so unlikely, 1.6% chance. Not impossible, but seems unlikely. All right, so again, so now for proportions problems, we check our conditions, normal and random. We find our center of our sampling distribution, draw the sampling distribution, and then based on our statistics, see where we need to shade, and then calculate the value using norm CDF. That's it. Let me know if you have questions.